Astronomy episode 270 for Monday, June 18th, 2012. Inertia. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Doing great. So actually, again, warping space and time. This is the second episode that we're recording on this day, which is actually in July, moments before the announcement of the Higgs boson, but as we're catching up shows. So we're actually only like a couple of episodes behind now.
Yeah,
we'll be caught up this
maybe
week,
Wednesday, maybe Friday we can record.
Yeah, we will be caught up.
Yeah.
And we will... I won't say that we'll never fall behind again, because we absolutely will, because that's just the reality. Yeah. So now we had a couple of people who posted sad reviews in iTunes because Astronomy Cast was a little bit late and they took away some stars from us. So we're really sorry for all of you who felt that us being late detracted from the Astronomy Cast experience. We understand that keeping this show coming out on a very regular basis is really important to you, and it's important to us, and we will absolutely focus our energy on getting this show out as regular as we can. Now, if you do love Astronomy Cast, or feel like you need to give a honest review, the iTunes reviews are a great place to do that. So you can just do a search for Astronomy Cast on iTunes, and you can give us a review. Be honest,
Yeah.
But it's great. Those reviews are wonderful, and we really appreciate them. So,
and we do read them and take them to heart.
We absolutely do, yeah. And in fact, the funny thing is, because I'm in Canada, I see a tiny version of the number of reviews, and I only thought we had a few reviews. And then I was able to switch my country to pretend like I was in the U.S., and then I could see all of the reviews. And it's like 1,000 or 1,500 reviews or something like that. It was quite overwhelming to see these all at the same time. The other thing that's really important to know is Google recorded a documentary about the virtual star parties that we do, which is really cool. So they actually flew a team of filmmakers out to all across North America, to our friends in North Carolina and in your house, Pamela, and my house here on Vancouver Island, and down in Los Angeles to meet with Gary, and they recorded this really moving documentary about the star parties that we do, and it's on YouTube, and you can get it from, I'm sure we'll put it into the show notes. But if you haven't seen this, it is unbelievable. It is really cool, and I highly recommend that everybody watches it. It's really neat. So, and if you want, remember, we always do our virtual star parties every Sunday night from, when it gets dark on the West Coast, for about an hour, hour and a half. We bring in a live view of telescopes. So we're trying to use all the different media in the appropriate ways so that people can appreciate astronomy as much as we do. All right, let's get recording. So an object at rest tends to stay at rest. An object in motion tends to stay in motion. Isaac Newton dismantled the traditional idea that objects would tend to slow down over time and described the concept of inertia, the amount an object will resist changes to its motion. Inertia. All right, Pamela. So then I think this is where we really kind of need to go back into history and get an idea. The traditional, the ancient Greeks, the medieval scientists, if you can call them that, what did they think about the way motion worked?
Well, the initial ideas actually go all the way back to Aristotle. And he thought that an object in motion would, over time, just stop. And he explained the motion of things like projectiles through the air as the medium that they were flying through, so in this case the air, was providing that extra something that was needed to keep them in motion while they flew. Now,
I didn't understand that. Hold on, what? The air was
the air was somehow going, keep moving, keep moving, keep moving. And so his idea was that if you were able to create a vacuum, objects wouldn't move through vacuums, which is a really weird concept.
So the air provided a way to propel objects forward?
It kept them in motion.
It kept them in motion somehow, but not accelerating. They would still slow down.
Well, and that was the crazy thing, was an object falling through air is clearly accelerating. A projectile goes up, arcs, and then accelerates back down. So somehow the air was responsible for all of this craziness.
Oh, so in other words,
force.
No, I understand, but so in other words, you go and you take an object up to the top of a cliff and you drop it. The air is going to be accelerating it towards the ground until it runs out of air and hits the ground.
And so there's something clearly funky going on.
Yeah.
The idea that in a vacuum things aren't moving. People who started thinking about the idea of a sun-centered solar system had a reaction to this. And so it was actually Galileo who initially started doing the hard experimental work to overturn this idea. Now, he wasn't the first one. So we had... well before that, we had Lucretius, who was working in the last century BC, who was trying to say that the default state of stuff isn't to be at a dead stop, which was Aristotle's idea, that if you left anything in motion, it would come to an eventual stop. He decided this probably didn't make sense. John Philoponus said that the idea of the median keeping things going, there were issues with it, and the void probably wouldn't limit motion.
Was this the theory, the impetus theory? Was this that?
Well, the impetus theory is all tied into it, and the impetus theory finally came out in the 14th century BC, and this was an idea that air is somehow pushing, and that when you give something energy, when you push it, when you accelerate it, you're giving it an impetus, and then that can get dissipated into the surrounding, well, this is where friction comes in, but they didn't have friction yet. Galileo is the one who really came up with a solution for this. And one of the big problems they have is they didn't have clocks. And so in Aristotle's thinking, and Aristotle did not believe in experimentation. Aristotle believed in thinking. And that a true understanding of the universe could come from thinking.
This is one of those classic examples, right? We had these ancient scientists, ancient Greeks, who would argue about the number of teeth that a horse had, right? And then somebody would go out and say, well, I'll just count them. And they're like, no, we don't do that.
And what's funny is sometimes it seems like there's very little difference between particle physics today and regular physics back then. Sorry.
Zing. Zing. In case people missed that, that was Pamela zinging the particle physicist. Well, send any letters to Pamela Gay, starstrider@gmail.com.
So you had all of these people philosophizing about how things move, and they actually believed that acceleration of a falling object was a linear process. So you go a distance, you accelerate n amount. You go twice that distance, you accelerate twice as much. And the reality is that it's a square relationship. So your acceleration, go 1 unit of time, you go 1 unit of distance. Go 2 units of time, it's going to be, so let me actually do 1 and 2 units of distance, 2 units of time, 4 units of distance. That does the math a little bit easier. Right. And so you have this square relationship going on, and you have to have a clock to figure that out. And it was Galileo who didn't solve the clock problem, but figured out a circumvention of it with what's called the water clock. If you have a very large surface area on a container, the rate at which the water level falls for small amounts is fairly linear over time. So you're getting a constant stream of fluid coming out. So every beat of the clock is a set of volume of water coming out. So what he did was he built this drum of water that had a system with water coming out the bottom that he could turn on and off. And he would very carefully weigh the amount of water that came out after a ball had gone a certain distance. And the one miscalculation that's in this is an object that's rolling actually has slightly different physics than an object that is sliding down, but it's such a small correction that it didn't affect the physics in this course.
Right, but this was a way that Galileo could slow down time. Essentially, he could make an object fall as quickly or as slowly as he needed to
using
be
an inclined plane.
Using an inclined plane, right? So that he could say, well, it's too fast for me to measure the stuff just dropping it, so let's use an inclined plane, and then I can measure the stuff in a much more slow, everything unfolds in slow time. Brilliant. Absolutely brilliant. We did those. Do you do that experiment with your physics students?
I don't do it at SIUE. When I was at Harvard, we did this, and we did everything we could to stay similar to what he did while not killing ourselves. So what he did was he actually used a many meters long inclined plane made out of a carved groove. He lined it with parchment to decrease the friction absolutely as much as possible. He created the water clock. He marked off the distances going down the inclined plane and measured how long it took it to go 1 unit of distance, to go 2 units of distance, and so on all the way down. Well, what we did, because, well, wood weighs a lot, is we used PVC pipe because that starts out nice and parchment smooth. And so we had things going down a half tube of PVC pipe that students used grease pencils to mark. And we did build our own water clocks using surgical hosing and those big old buckets that you get when you're tarring your driveway.
So then what is the relation to inertia, though? How does this play into the story that we're telling?
Well, what he figured out as he decreased friction as much as possible is that when you sent something going down the inclined plane, it would just keep going down the other side if it was flat. But if he ended up with 2 back-to-back inclined planes and decreased the friction as much as possible, it would go up to basically the same starting height. So he was able to take how much potential energy, and he didn't have these concepts. It took Newton to get to gravity. But he could start it off at the top, it would accelerate down, and then it would decelerate up. And as he lowered the plane, it went further and further and further. So he was able to say that whatever was needed to go up that incline dissipated the motion. But if there was no force, if there was no something acting on the object, it would keep going forever. And he actually, in writing about this, trying to explain the concept of friction, he had some great discourses where he was basically, he had different characters arguing over what friction was, and this is where the little demons argument comes in, where there were people basically saying that there's little demons out there that are stopping the things and getting them to stop moving, and that when you smooth something off, you're clearing the demons off, and things like that. And
smoothing things off to clear the demons off.
It's a brilliant, if you ever have a chance to read the discourses that Galileo wrote, they're brilliant, and you can instantly see why he got himself in so much trouble with the Pope.
Yeah, if people haven't read these, they absolutely should. I'm sure it's all available open source out there somewhere.
It should be. There's a great source of Galileo-related everything at Rice University.
And he wrote in a very accessible style, and he was clearly poking fun at the people who disagreed with him, who also happen to be very powerful people who were able to put him in jail. But that's that's a whole separate show that we've already done on Galileo. So Galileo gets to the point that he's created this. He's figured out that there is some kind of inherent motion that is accumulated by the object rolling down the hill, which it then dissipates again as it goes back up. So how did this sort of carry the concept of inertia forward?
So we went from an Aristotelian view of the universe in which an object in motion comes to a stop, to or something, to a way of else acts. Finally started to get friction, we finally started to get gravity on it. To eventually, when Newton came along, it became an object in motion stayed in by an external force. Unless they're worked on by an external force as well. And this was one of those things that folks really struggled with, because with view of they keep going in a straight line, but why do the planets keep orbiting? That was a serious challenge that Newton had to figure out how to address, and that's where gravity became such an important part of understanding inertia, basically.
Right, and so if Aristotle had really just thought a bit and looked up and noticed that the planets are flying through space, of course he didn't know that there was no air up there, right? They thought it was like some kind of ether, I guess, right?
Well, and he had them embedded on spheres.
On spheres, and spheres, which, okay, never mind. See, he never would have figured it out. But the point being, right, that the point being that you've got the situation where you've got these objects, they are moving, and yet they're going in a circle. Why don't they stop? Why don't they spiral outward? Why don't they spiral inward? What's going on, right?
And this is where we had to understand that the force of gravity connects 2 points at their center of mass. And if my microphone here is the planet Earth, and this rock is the moon, then Earth, and that would be a very straight into the Earth. But because the moon has a velocity that's trying to carry it forward, gravity is constantly pulling it in, causing it to constantly arc inward, but it has enough velocity so that it never hits the Earth. So it's trying to go straight. Gravity is trying to pull it down, and we're having really terrible lag. I'm really sorry for all of you who are watching.
So just to warn you, Pamela, you're having horrible lag.
Okay, we're now like 10 seconds out of.
Can you solve it? Do you know what's going on in the house?
No, I have no idea what's going on. There's construction work going out on the street.
But your husband is definitely not using a ton of internet there?
No, I checked with him.
We can hope that this will pull together. We're about halfway through the show right now.
Okay, I'm going to stop moving unless required. I can still hear you just fine.
The other option is you can mute your video.
If I stop moving unless I have to, that will help.
Yeah, you're starting to stabilize again right now.
Okay, I will simply stop moving anything but my face.
But then we'll lose all your hand gestures.
Yes, but at least you'll have my face, which is better than a big black box.
Yeah, I think you're okay. I think the lag has gone away. The lag monster has run out of food and moved on. So I think you're okay. No, wait, no, you're totally lagging again. You're going to have to go to a black screen.
Yeah. So, okay,
go to
I'm
black
going
screen.
to stop moving. Okay.
So, can you hear me still?
That will help, but even the black screen initiation, I can hear you just fine, but there's this huge lag. Like, I clicked the video button, it took it like 10 seconds.
Do you want to leave and come back?
Do you want me to just rejoin the Hangout?
Yeah, why don't you leave and come back? Shall I stop my recording? Okay. You want to just keep your recording going?
Yeah, I'll do that.
Okay, I'll stop mine. Well, hi, everybody. Yeah. See, the thing is, like, this is the kind of crazy silliness that happens during many recordings of Astronomy Cast. I would say, there's a lot of times when there would be, like, upstream lag through Skype or whatever, and I would ask Pamela a question. She would answer the question, and I think I know what she said, but the lag gobbled it away. So I kind of have to try and take off from where I think she's finished, because I kind of know where she was going. So sometimes it works, sometimes it doesn't. Now the trick is that you don't hear it in the final version of the show because we record our separate versions of the show onto our own computers, and so we get the source directly onto our computers, and so we don't get any of this lag. It's just we have the lag for the communication, and it's the lag that happens in the stored version of Astronomy Cast. So we'll see. Perhaps a Higgs boson got caught in the wire. Perhaps.
Okay, we'll see if this is any better. It was lagging to the point that I'd say something, and then you'd ask me the question that I had just answered.
Yes. All right. So when last we saw our heroes, we were talking about planets. So where do you want to pick us up again?
Do you want me to try and explain gravity and inertia again?
Well, did you feel like you recorded it?
I recorded it. So do you want to pick up with I explain that?
Well, should we? Okay, so what kind of question will I be? What question got answered in your mind?
I was explaining the fact that Galileo had inertia with things moving in straight lines, but then there was this crazy problem with planets moved in circles, and they needed something, and Newton needed to come up with a force for that.
Right, and I sort of reiterated what you said and said, right, so we've got the situation where...
Should I press record? Should you press record?
Not yet.
Okay.
Not yet, until we decide where we're going to start.
Dear audience, we're so sorry for all the sausage today.
Somebody says, can we make orders for sausage we're watching? I'd like some Bavarian wurst. Yes. Yes, we're taking lots of orders. We'll make some hot dogs, we'll make some sausages, you name it, we'll make it. Right, so why don't we go back to that? So I'm going to reiterate again. I'm going to reiterate what you said, and I'm going to say something to the gist of just how the planets, that you've got the situation, why don't they spiral inward, why don't they spiral outward, and then, and then you can just go wherever your brain. Okay. Okay? Okay. All right. Okay. I'm going to press record. You press record. I'm at the 1843 mark.
Yeah, I'm at 1846, so Preston will live.
Okay, do you want to sync it up just to be safe?
Yeah.
Okay.
So.
I'm pressing record.
Okay.
Okay.
Should we do, say 1, 2, 3?
Sure. We'll do this in 3, 2, 1. There. Okay. That never works.
Poor Preston.
This recording is a brand new... Okay, never mind. I'll figure this out later.
Okay.
Okay, so watch this, everybody. Right, so you've got this situation where you've got these planets that are moving, that nothing's slowing them down. They're not spiraling outward. They're not spiraling inward. What is the force? Why are they kept going in this circular orbit around the Earth? And this is the concept of gravity and inertia.
And so this is where, for a while, there was actually people thinking that inertia wasn't just an object in motion, stayed in motion in the same way, but an object in motion could either stay in motion in a curve or in a straight line. Well, today we now know that an object in motion will stay in motion with the same vectoral motion that it had to begin with unless acted upon by an outside force, and a vector defines both its speed and its direction.
But in the case of the planets, of course, they're orbiting in a circular vector. I mean, they've got multiple forces pulling on them, right?
So the thing is, vectors are straight lines, but then you can define them across, well, a vector is something that has multiple characteristics. So velocity is something that only has a speed and a direction. The planets are actually accelerating, which means their exact velocity is constantly changing because that direction is constantly changing.
Right.
Now, if an orbit's a perfect circle, then its speed is constant at all times, but its velocity is constantly changing as that direction changes.
Right, right, okay. So where did sort of Newton's sort of main discovery come in?
Well, the story, as frequently told, is he was sitting under a tree and saw an apple fall and saw the moon in the sky and had this epiphany that a falling apple and a falling moon are the exact same thing, except the moon is missing the planet. And the analogy that often gets used is if you have a cannon and you put the cannon on a hill, when you fire the cannonball, if you have it with sufficiently low velocity, it lands on your foot, assuming you're standing right in front of the cannon. If you hit it with larger force, it goes a larger distance. If you hit it with larger and larger force, it goes a larger and larger distance. And it always arcs down to the planet, though, as it falls, because gravity is constantly trying to pull that cannonball back to Earth. Well, if you use enough force to fire that cannonball, it's going to gain sufficient velocity that Earth's pull only succeeds in bringing it around so that you hit the butt of the cannon. Now, if you hit it with even more force, you can actually start to hit escape velocities, and this is what we do with rockets, in which case the force of gravity is insufficient to change the initial velocity sufficiently to get the cannonball to return to the planet.
So then, I mean, he really famously coined that phrase, right? That a body in motion tends to stay in motion, and an object at rest tends to stay at rest. So
unless acted upon by an external force.
Unless acted upon by an external force, right? Exactly. So how did this sort of change people's understanding of the objects moving around them?
Well, it was a sudden epiphany that everything is connected by forces, and that when we see something happen, one of two things has to be true. There's either a force acting on the system, or we're looking at a system that's undergoing acceleration. And this is where we start to get into inertial and non-inertial frames of reference. So if you're in an accelerating car, that's a non-inertial frame of reference, so that when you look at the hanging dice hanging from your 1970s vintage automobile's rear view mirror, you'll see the dice don't hang straight down towards the center of mass of the planet Earth. As you're accelerating, they will actually sway backwards, and that's because it's an accelerating frame of reference. And an inertial frame of reference is one in which there's no acceleration taking place.
And this is why, as you go around a corner, you feel pushed up against the side of the car, right? Because you tend to want to stay in the motion that you were going, which in this case, you wanting to move straight forward. But the car is now exerting an external force on you, on your left shoulder, that is pushing you around the corner with it, and so your body is pushing back against the side of the car, and that's what you feel.
This is where crazy fictional forces come into play, because as your car whips around that corner, as little kids in the back seat always know, because you try to purposely smush each other into the door, you feel like you're getting forced to the outside of the car, but the actual force is towards the center of the circles. So this is why when you have a ball on a string, the ball stays on the end of the string. It's because the force is going towards the center of the circle. Now, there's this sudden, wait, hold on, but the kids are flying outwards. Well, no, the kids are simply trying to go in a straight line, and the car is getting in the way of that straight line. And so what you're experiencing is this frictional force on your butt. Your body's trying to keep going straight forward, and as the car curves, you're getting caught by friction, basically. And that's, you want to go in a straight line. You're failing to go in a straight line. The car is preventing you from going in a straight line. You feel like you're getting flung outwards. The reality is the real force is towards the center of the circle.
Now, this was all fine and good, and completely changed everyone's thinking about the universe and the motion and physics, and helped lead to the steam age and all these great technological investments. And thanks, Isaac Newton. But this was all sort of thrown up, was sort of thrown out the window again when Einstein came along.
Well, it wasn't so much thrown out the window as it was changed. So as we started trying to figure out frames of reference, as we started trying to figure out what is an inertial frame, suddenly in a relativistic situation, things started to become much more curious. So suddenly when you're looking at your frame of reference, you realize every observer has their own frame of reference. You start to realize everything's in motion. You start to realize there is no such thing as a truly inertial frame of reference. I mean, we can pretend that we have a non-accelerating frame of reference. If you're standing next to a railroad train and a railroad train goes by and you see someone drop a ball in the window, relative to the moving train, that ball falls straight down. Relative to you, you'll see it starts falling here, it lands over here because the whole window moved sideways. So within the train, it seems to be a non-accelerating inertial frame of reference. You can go back and forth between the two frames of reference, but you're on the surface of a planet going in a circle, which means you're actually constantly changing velocity as you stay adhered to the surface of the planet, but over a small distance. We're able to make these assumptions. But when we start looking at larger and larger distances, we start having to worry about things like Coriolis force. we start having to worry about the effects of the fact that the planet is rotating underneath you. And all of these different things start to come together, and life gets more and more complicated. Now add to that the effects of time contraction, add to that all of the relativistic effects, and suddenly defining inertial frames is a nightmare because they don't totally really exist, and every observer is their own observer.
And that's where the headaches start to set in.
Yeah.
Yeah. But, of course, the predictions made by Einstein perfectly match the measurements that are made in space to a level of accuracy that Newton could have only dreamed about. And so...
Yeah. And one of the beauties of all of this was this realization that whenever we're dealing with things, the proper way to think of them isn't an object of a given mass moving at a given velocity. It's to think of it as an object with a set amount of momentum, because it's the momentum that things carry with them that has the true impact, just to be unintentionally punny. And so the example I use in class a lot is you can imagine a 3-year-old and a sumo wrestler on roller skates. If that 3-year-old starts going as fast as it can, skating towards the sumo wrestler, it's carrying a set amount of momentum that it's going to impact into that sumo wrestler who, assuming no friction, no inelastic parts of the collision, they're going to bounce off of each other, and the sumo wrestler is going to be basically unaffected, and the 3-year-old's going to go flying off in the opposite direction. Now, if you instead have 2 sumo wrestlers doing this, you're going to end up with, perhaps if you get a second equal mass sumo wrestler coming along and hitting at the same velocity as that small child was, well, that big other sumo wrestler is now going to take all of that velocity and start going in the same direction, and that first dude will stop cold, just like a pool ball will.
Yeah, a pool. I was going to talk about that pool ball example, right? Which is a wonderful example of this transfer of inertia, right? You have a ball sitting on the table.
Transfer of momentum.
Transfer of momentum. Sorry, and you shoot your cue ball at that ball. That your cue ball, in a perfect world, stops perfectly, and now that second ball is moving.
And the key to achieving that perfect world is to have the 2 centers of mass completely line up so that when it hits, all of its force goes straight into an impulse on the other one, and all of the momentum gets cleanly transferred. Now, the reality is that most of the time when you hit pool balls together, it's not that perfect center of mass, and you end up hitting slightly off-center. And so this is where you hit it, and it veers off. And if you get good, you can actually hit something with a glancing blow and cause it to go off at close to a right angle.
That is really cool. All right, well, I think we made our way through this episode of Inertia. So once again, thank you very much, Pamela, and we will see you next week.
I'll see you next week, and hopefully the internets will be with us.
Yes. All right.